Hey everyone, this is Sunil Kumar Garpati. Here I am going to explain about a research paper based on a comparison of approaches to large-scale data analysis under Professor Kwang Soyan. Coming to the introduction, recently the trade press has been filed the news of a revolution of cluster computing. This paradigm entitles harness large number of processors working in a parallel to solve a computing problem. In effect, this suggests constructing a data center by lining up a large number of low-end servers instead of deploying a small set of high-end servers. With this rise of interest in clusters has come a proliferation of tools for programming them. One of the earliest and the best known such tools is MapReduce. Interesting trade-offs as revealed by the results with the parallel DBMS exceeding MapReduce in terms of observable performance but requiring more time to load data and fine-tune execution. The study analyzed implementation ideas for further systems and offer insights into the benefits and drawbacks of each technique. Slide. The two approaches to large-scale data analysis are MapReduce and parallel DBMS. Coming to the MapReduce, one of the attractive qualities about the MapReduce programming model is its simplicity. An MR programming consists only of two functions called map and reduce that are written by a user to process key value data pairs. The input data is stored in a collection of partitions in a distributed file system deployed on each node in a cluster. The program is then injected into the distributed processing framework and executed in a manner to be described. Coming to the parallel DBMS, database systems capable of running on clusters of sharing nothing nodes have existed since the late 1980s. These systems all support standard relation tables and SQL, and thus the fact that the data is stored on multiple machines is transparent to end-to-end users. Many of these systems build on the pioneering research from the Gamma and Grace parallel DBMS projects. The two key aspects that enables parallel execution that are most tables are partitioned over the nodes in a cluster and that the system uses the optimizer and the translator SQL commands into a query plane whose execution is divided among the multiple nodes. Because the programmer only needs to specify their goal in a high-level language, they are not burdened by the underlying storage details, such as indexing options and join strategies. Working of parallel DBMS. Consider an SQL command to filter the records in a table T1 based on a predict, along with a join to second table T2, with an aggregate computed on the result of the join. A basic sketch of how the command is processed in a parallel DBMS consists of three phases. Since the database will have already stored T1 on some location of the nodes partitioned on some attributes, the filter subquery is first performed in parallel all the sites similar to the filter performed in a map function. Following the step, one of the two common parallel join algorithms are employed based on the size of data tables. For example, if the number of records in T2 is small, then the DBMS could replicate it on all nodes when the data is first loaded. This allows to join to execute in a parallel at all nodes. Following this, each node computes the aggregate using its portion of answer to join. The final roll-up step is required to compute the final answer from the partial aggregations. If the size of the data in T2 is large, then T2 consists will be distributed across multiple nodes. If these tables are partitioned on different attributes and those used in the join system will have has both T2 and the filtered version T1 on the join attributes using common hash function. One each node has the necessary data in the performs a hash join and calculates the preliminary aggregate function. Again, a roll-up computation must be performed at last step to produce the final answer. At first glance, these two approaches to data analysis and processing have many common elements. However, these are notable differences than we considered in the next section. And coming to the architectural elements, it consists of schema support, indexing, programming model, data distribution, flexibility, and fault tolerance. Coming to the next slide, why is it important? The research paper's topic is significant since it has to do with the machine learning model optimization, a crucial undertaking in the field of artificial intelligence. The study specifically addresses the issue of hyperparameter optimization, which is a crucial step in creating precise and effective machine learning models. The issue is crucial since a machine learning model's effectiveness significantly depends on the choice of suitable hyperparameters, which can have a big effect on models' efficiency and accuracy. Therefore, enhancing the hyperparameters optimization processes can result in stronger machine learning models and eventually improved performance across a variety of applications, from the computer vision to natural language processing and beyond. Coming to the next slide, is it a hard problem? What is the novelty of the research paper? Yes, it is a hard problem because generating diverse and high quality responses in open domain conversational agents is challenging due to high dimensional nature of language and the need for balancing multiple objects such as fluency, relevance, and diversity. The novelty of this research lies in the proposed framework that jointly optimizes the response generation model and diversity promoting objectives. Moving on to the next slide, what is the main contribution? There are a number of interesting conclusions that can be drawn from the results presented in the paper. First, at the scale of the experiments we conducted, both parallel database systems displayed a significant performance advantage over Hadoop MR in executing a variety of data intensive analysis benchmarks. Average across all 5 tasks at 100 nodes. DBMS-X was 3.2 times faster than MR and Vertica was 2.3 times faster than DBMS-X. While we cannot verify this claim, we believe that systems would have same relative performance on 1000 nodes. The dual of this number is the parallel database system and provides the same response time with a far fewer processors will certainly uses far less energy. The MapReduce model on multi-thousand node cluster is a brute force solution that wastes the vast amount of energy. While it is rumored that the Google version of MR is faster than the Hadoop version, we did not have the access to this code and hence could not test it. We are doubtful again, however, that there would be a substantial difference in the performance of two versions as MR is always forced to start a query with the scan of entire input file. Although we not surprised by the relative performance advantage provided by the two parallel database systems, we were impressed by how easy Adobe was to set up and use in comparison to the database. The vertical installation process was also straightforward but temperamental to certain system parameters. The DBMSX, on the other hand, was difficult to configure properly and required repeated assistance from the vendor to obtain the configuration that performed well. For a mature product such as DBMX, the entire experience was indeed disappointing. Given the upfront cost advantage that Hadoop has, we now understand why it was quickly attracted such a large user community. Coming to my approach, it involves training a response generation model using maximum likelihood estimation and using a diverse promoting objective to encourage the model to generate diverse responses. And also the author uses a beam search algorithm to sample diverse responses from the model during interference. Yes. What is the validation? The validation of the proposed approach involves comparing it with several state-of-art baselines on multiple metrics such as diversity, fluency, relevance, and human evolution. The experimental results demonstrate that the proposed approach outperforms the baseline on all metrics, indicating its effectiveness in addressing the problem of the response repetition in open domain conversational agents. Thank you.